Good morning, our students, and welcome to this early hours class. Today, we'll be continuing to look at a very powerful topic in statistics called analysis of variance. In our previous class, we had a very robust or a very good introduction of analysis of variance that spanned through the definition of analysis of variance, different kinds of analysis of variance that we have in terms of whether the groups are independent or whether they are dependent, and then the number of factors that are what involved in it. So we encourage you that perhaps you call that class up and be able now to go through it before joining in this particular class. However, the kind of discussion we are going to have in this one, actually, your understanding of this class might a little be independent from what we had before, because we are going to be very detailed. Now, the particular topic that we have under the analysis of variance today is what we call one-way analysis of variance independent group. One-way or one-factor analysis of variance independent group. One-way, what we call one-way. Or we call it one-factor analysis of variance. Analysis of variance. We open a bracket, ANOVA. Independent groups. Independent groups. Independent groups. Don't panic, because we are going to explain this in a way and manner that you understand exactly what we are about to do. In our previous class, we did say that the short form of analysis of variance is ANOVA. So any day you see ANOVA, we are referring to analysis of variance. And what we have today is one way or one factor analysis of variance. So the question becomes, what do we do in one way or one factor analysis of variance? By a way of definition, in one way or one factor analysis, of course, it is a statistical test that helps us to determine if there is any statistical significant difference between the means of two or more independent groups, or between two or more independent levels of a factor. I repeat, so I will be able to bring out keywords from this definition. I said, in one way or one factor analysis, it is a statistical test, number one. It helps us to determine if there is any statistical significant difference between the means of two or more independent groups, or between two or more independent levels of a factor. That is by way of a definition or explanation. What are the things that we need to know about this one way or one factor analysis? What we need to know about them is this. Let me bring them out. Number one, how many factors are involved in one way or one factor analysis of a variance? Like the name applies, one factor. So the number of factors involved here is what? Is one. So I have one factor analysis of variance. So the number of factors there is one factor. The next question there is, we said between two or more levels of a factor to determine if there is any statistical significant difference between the means of two or more independent groups, or between two or more independent levels of a factor. So the question is, in one-way analysis of variance, how many levels of factor is involved? Going by the definition, we said two or more independent groups, or two or more independent levels of what of a factor. So in one-way analysis of variance, the number of levels of the factor could be 2, it could be 3, it could be 4, down the line. Begins from 2 down the line. And of course, we don't know when it's going to be 2, we don't know when it's going to be 3. So it is better now we talk about a number to assign to this group, such that, a value to assign to this group, such that that value can change. The value can become 2, it can become 3, down the line. So we can talk about k levels of a factor. K independent levels of a factor. Where this k could be 2, where this k could be 3, down the line. So how many levels of the factors now involved? Let us go with k levels of a factor. So I have here to be k levels of a factor. K levels of a factor. And remember that this k can be 2, it can be 3, down the line. Because the definition says 2 or more. Okay. And that thing is, these levels of the factors, levels of a factor involved here, what are their nature? Their nature is they are independent groups or independent levels. So the factors involved here are independent. Independent, permit me to write this as independent. Independent groups or levels. Independent groups or levels. And that thing we are going to look at from the concept of this one factor, one analysis of variance, is what we call replication. Replication. And in the replication, we are saying, how many times did we repeat the application of a particular level of a factor on the experimental unit? How many times do we repeat it? It can be twice, we don't repeat, we don't do once. It can be twice, it can be thrice, down the line. So in that case, it is better we say that we have n replications. We are going to replicate it up to n times. For us to understand what I have said about one factor, k levels of a factor, independent groups, and replication, we are going to show what we call one-way or one-factor data layout. One-way or one-factor ANOVA data layout. With that, everyone will understand what we mean by these effectively. So permit me to clean the board while we show the data layout of a one-way analysis of variance. So permit me to clean here. Let us begin by using a factor which might be very familiar to all of us. And let us call that our factor now. Fertilizer is our factor. Remember that in our previous class, we say that a factor is any variable that the researcher is interested to study its effects in an experiment. Of course, when you are a farmer and you are applying fertilizer to your crops, and you are observing the growth of your crops, invariably you are observing the efficacy of the fertilizer. So in this case now, fertilizer is our factor, or what we call the independent variable. So I will now come here and I'll write what fertilizer. Permit me to write fertilizer as F-E-R-T dot. I am referring to this as what? As a fertilizer. And of course, you know that there are different kinds of what? Of fertilizers. There are different kinds of what? Of fertilizer. Ranging from what we call the NPK fertilizer. So let me represent the NPK fertilizer with something like what? 1. We equally have what we call nitrogen fertilizer. I will represent it with what we call what? 2. And there are so many other kinds of fertilizer. So it is ranging up to what? K number of what? Fertilizers. And each of these NPK, nitrogen fertilizer, down to this K level of what factor, or this K fertilizer, is what we refer to as levels of this factor fertilizer. So here, my NPK is a level of this factor fertilizer. My nitrogen fertilizer is a level of this factor fertilizer. Down to the Ket fertilizer, which is of course a level of this my factor fertilizer. So that was why we said that we use it to determine if there is any statistical significant difference between the means of 2 or more levels, independent levels of what? Of a factor. And we said, because we don't know whether it is going to be 2 or whether it's going to be 3 and the rest of them, let us use what? K, where K can take up what? Any value. So in that case now, we now have what we call K levels of what? Of this factor fertilizer. The next question is, each of these fertilizer level will be applied on experimental units. And in this case, let us call it what? Crops, particularly maize. And we are interested in observing the yield or the quantity of growth that is recorded in these crops called maize. So let me now come here and have what we call replication. Replication. And then that replication, of course, let me now put what? J here. Let me put J here. And that J here is beginning from what? 1. Let me put J. And that J here is beginning from 1, from 2, from 3, down to what? To N. And of course, let me use here to be my I, where my I begins from what? 1, 2, down to what? To K, which stands for what? The number of what? Levels of the factor. This one is standing from number of what? Replications. So if I come here and I'm talking about the quantity of yield that I obtain from the first maize stand, when I apply the first level of what? Of factor, let me represent it with what? Y11. I am at the second maize stand, which is of course the replication of this first treatment on experimental what? Units. Because these maize stands that is beginning from 1 to what? N are what we call experimental unit, which of course is the maize stand, upon which we apply our experimental treatment or level of a factor NPK. So here I have what we call Y12. The second observation from the first level of what? Of factor. Here I have what? Y13. The third observation from the first level of what? Factor down to Y1 what? N. The nth observation from the first level of what? Of a factor. Then I also come here, I have what? Y21. Then I have the first observation from the second level of a factor. We have what? Y22. Second observation from the second level of a factor. Y23. Third observation from second level of a factor down to Y2n. nth observation from the second level of a factor. So this thing goes down to what we call yk1, first observation from the kth level of a factor, yk what 2, second observation from the kth level of a factor, yk what 3, third observation from the kth level of a factor, then we have ykn, nth observation from the kth level of a factor. So while I have I here, I runs from 1 to k, talking about the number of level of a factor. While I have j here, j runs from 1 to what, to n, talking about the replication of the experimental units. The number of experimental units now that I replicate each of these level of factors on. So how many replication here? N replications. How many levels of a factor here? K levels of what, of a factor. There is something you need to understand here. What you need to understand here is what I want to show. If you have observations this way, you have 1, you have 2, you have 3, you have 0, you have 2, you have 1, you have 1, you have 1, and you have 2. And you are to count the number of observations you have here. You count it this way. 1, 2, 3, 4, 5, 6, 7, 8, 9. The total number of observations is what? Is 9. So this equals what? 9. And there is also another way on how to arrive at this 9. And that way is to ask yourself, how many rows are here and how many columns are here? The number of rows are 1, 2, 3. Number of rows is 3. Number of columns are how many? 1, 2, 3. 3 times 3 is what? 9. So when data is arranged in rows and columns, to obtain the total number of observations there is the number of rows multiplied by the number of what? Columns. And if you come to this data layout, it is equally arranged in rows and what? And columns, represented by the number of what? Levels and the number of what? Replications. How many number of levels do I have? K number of levels. How many number of replications do I have? N number of what? Replications. So if I want to get these total observations here, it is going to be K, which is the number of the rows, multiplied by what? N, which is the number of what? Columns. So my total observation here now becomes total observation, total OB equals K times what? N. What if now somebody tells you that the total observation is what? Is 15. Total observation is what? Is 15. And the number of what? Replication is what? Is 3. Number of replication is what? Is 3. And the person asks, how many levels of factor do we have there? How many levels of factor do we have there? The total observation is 15. The number of replication is what? Is 3. And remember that replication is what? Is n. So we are now going to say what? K times what? 3. And of course, you know that this K is talking about the level of what? Factors. So for you to make this to stand all alone, you divide both sides by 3. So this is all over 3. This is all over 3. This will cancel this and you are left with K. 3 here is 1 and 3 to 15 is what? 5. So the number of level of factor there is what? Is 5. So what if somebody says, if the number of what? Replication is 3 and the number of what? Factors, or the number of levels of what? Of the factor is what? 5. What is the total observation? It becomes 3 times 5, which gives what? 15. So a lot of questions can come from here regarding on total number of observations, number of levels of what? Of a factor, and replication of each level of what? Of a factor. So you have to pay attention to that. Okay. That's by the way. So permit me to clean this. On the course of computation of the ANOVA table, which of course we are yet to discuss, There are certain things that we need to understand from the data layout, which of course will be assisting us now when we get to that stage. And what I want us now to understand here is this. If I put a line here, remember that this my 1 is level 1, or what we call group 1. This my 2 here is talking about level 2, or what we call group 2. Down to what we call level K, or group what? K. What if we are required to find what we call the group levels, or what we call the group totals? Not group levels, group totals. Group totals means you come here, you sum all the observations in a particular group. You write its value here. You come down to this particular level, you sum all the observations here, you drop it here. And whatever thing you get here is talking about what? The group level, which is now the first group level. Whatever thing you get here is the second group level, down to here, which we call the third group level. Permit me to write here, which of course I'm going to explain, yi dot. In analysis of variance table, when you sum observations over something that is changing, you use a dot to represent that you have summed over something that is what? That is changing. How do I mean by that? Let us come to group 1. We want to get what we call the group total together. By that, we are going to say y11 plus y12 plus y13 down to y1n. So let us now write here what? Y. Permit me to show you that this 1 here, 1 here, 1 here is constant. It is not changing. Referring to the first level of a factor. So let me now write that 1 that is not changing to be here. And I had earlier said that when you sum something over what is changing, you use a dot to represent that. What is changing here is the column. The number of column here is 1. But when you come here, the number of column has become what? 2. If you come here, the number of column has become 3. So the number of column is changing. And because the number of column is changing, you use a dot to represent that column, showing that you have summed the observation over the number of what? Columns that are changing. So you have what we call dot here. This y1 dot is the total of everything that is in this group 1. This 1 I wrote here is talking about what? Group 1. The dot here is referring to us that I have summed these observations now over these columns that is changing. That is the essence of this dot. So here I will equally come and have here y. The 2 is constant, it's not changing. So I have right 2. But the column is changing 1, 2 down to n. So I put this dot dot. I have y k dot. This my y1 dot, y2 dot, and yk dot. We refer to them as group totals. In case they ask you to obtain the group totals, these are the group what? Totals. And then we equally have what we call the group means. Group what? Means. And permit me to equally now put a line here and talk about what we call yi dot bar. When you talk about what? Bar, you are talking about what? The mean. Okay? And remember that for you to get the mean of observation, it is total of the observation divided by the number of observations. Okay? So the total observation here, you have already gotten them here. What is the number of observations here? N. So if I want to get this group mean here, it is going to be that my y1 dot bar is given as what? Y1 dot all over what? N. How do I mean by this? This is already your group total. Look at it here. The number of your observation is what? Is n. So group total divided by number of observation will give you group mean. So that's what we mean by that. So in that case, here is going to be y2 dot bar is going to give me what? Y2 dot all over what? N. Down to what we call yk dot bar, which is going to be what? Yk dot all over what? N. So this my y1 dot bar, y2 dot bar, down to yk dot bar. We refer to them as the group means. In case they ask you to obtain the group what? Means. Okay? Now, there is equally another thing that I want to show you here. Let me put a line this way. And then, I want us to look at this. We refer to this as what we call the group totals. Permit me to equally put a line this way, so it won't be confusing you. Now, we call this one our group totals. Group totals. What if we are interested in the grand totals? That is the total of all these observations here. We come here. This is the group total for the first one, group total for the second one, group total for the third one. So if we sum all these group totals this way, it is as good as summing all these observations here. And there is something I want us to observe together. Watch me. If you come here, you are going to say y1 dot plus, y2 dot plus, down to yk dot. Something is now changing here. So I'll first of all write what? Y. I am saying y1 dot plus, y2 dot. If you notice here, the number of rows now are changing from 1 to 2 down to k. And once we are summing over anything that is changing, we use a dot to represent it. So I will put a dot in place of what? Column. Sorry, in place of what? Row. We ask ourselves, what is it that is constant here? What is constant in all these things is dot. Dot is here. Dot is here. Dot is here. But because it is constant, we just bring it down. So I have another dot. Just like when we are doing this. This my 1 was constant everywhere. We brought it here. This 2 was constant. We brought it here. Because this my dot equal is constant, I brought it down here. The first dot is referring to what we call summing over the rows that is changing. This my y dot dots is what we call the grand total. We call it what? The grand total. Y1 dot, Y2 dot, down to YK dot. Group totals. Y dot dot, grand totals. So this is actually explanation that we can give over what we call the one-way data layout of analysis of variance. Let us pick one example and showcase what we mean by this group total, group means, and the rest of them. So permit me to quickly click here and show something. What if now we have a factor, and that factor we have a factor. That factor we have first level A, it has B, it has C. Then it has a rep. The rep it has is what? 1, 2, 3. And you have observation here 0, 2, 4, you have 9, you have what? 7, and you have 1. Then you have what? 2, you have 0, and you have 8. And someone asked that I should obtain the group totals and equally obtain the group what means. And equally tell us the total number of observations that you have. Tell us what the number of replications. And equally tell us now the number of levels of factor, which we have from this. How many levels of factor do we have? We have 3. 1, 2, 3. Which is what? Level A, level B, and level C of this factor. So the number of levels we have of factor, number of levels equals what? 3. How many replications do we have? That is the number of times we replicate each of what? Of the levels. Look at my level A. How many times was it replicated? 1, 2, 3. That's what I see here. 1, 2, 3. So the number of replication is what? Is 3. Number of replication. Number of replication equals what? 3. Then someone says, now what is the total number of what observations here? Total number of observations, like I said before, is number of what treatments or number of levels multiplied by number of replications. So total observation is given as what? Number of levels, which is 3, number of replication, which is 3. So this will give you what? 9. Okay? So these ones are not difficult to what to answer. Number of levels, 3, number of replication, 3, total number of observation, 3 by that will give you that. So I'll book in clean this one. Permit me to book in clean this thing. For us now to get what is called the group totals and then the group means, we have our line like this. So we now talk about what we call group totals. Group totals. We can use our yi dot to represent it as well. Yi dot. Yi dot. And in that case, you quickly tell yourself that this is here I and here is what? J. You quickly tell it that way. So we are going to sum this way. Okay? So summing this way, we have 0 plus 2 is 2 plus 4 is what? 6. 9 plus what? 1, 10 plus 7, 17. And then this plus this is what? 10. So these are the group totals. 6, 17, and what? 10. Then when we now talk about the group means, we now talk about what we call yi dot bar. And remember that we say that y now, the level here is now for A. So our ya dot bar is given as what? Our y, this 6 here is now going to be given as what? 6 all over what? Our number of replication. Number of replication is what? 3 all over 3. So this will be able to give me what? 2. For this one, I have that yb dot bar is going to give me 17 all over what? 3. I think that should be 6 point something or thereabouts. So you come this way, it becomes what? Y dot c dot bar is going to give you what? 10 all over 3. Whatever this value gives you is what we call the group means. Okay, that's by the way, so that we don't spend so much time there. So if they ask you about group A, then if they ask you to obtain the grand total, you come here and then you write that your grand total is y dot dot equals. It says 6 plus 10, 16. 16 plus 17 will be able to give you 31, I guess. So you have 31. This to this is 16, so you have 16. And then this to this, you have 17 here. This plus this gives you 13, right? 3, carry 1 to here, 2, which is have 33. So your grand total is 33. The grand total is 33. Thank you very much. Let us move an inch once again. Okay? We have been able to show the data layout for one-way analysis of what? Of variance. And we want to believe that you understood everything that we meant by that data layout. So the next thing here is what is the model for one-way analysis of variance or one-factor analysis of variance independent measurement? What is the model for it? The model for it is given as what we call Yij is given as what? Mu plus. We have alpha what? I plus Eij Don't be scared by what we are writing. This, of course, is referring to what? To the mean. This is referring to the what? Height effect of the treatment, or height treatment effect. Height treatment what? Effect. This EIJ is the error term associated with the observation YIJ. So this is the model for one way or one factor analysis of variance. You see that the number of words factor that we have here is just referring to one. That's why we are talking about only the height effects of treatment I, or what we call the height treatment effect. Height treatment effect. So if we have another factor now, we could have talked about I treatment effect or J treatment effect and the rest of them. So the next thing becomes, what is the assumption of these models? What is the assumption of these models? The assumption. The assumption is straightforward. Now the assumption says, number one, that all the variables in this model have to be normally distributed. All the variables, all variables in the model have to be normally distributed. Normally distributed. Have to be normally distributed. Number two, they say all the variables in the model have to be independently and identically distributed random variables. Say all the variables, all variables in the model have to be independently 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 and identically distributed random variable. Distributed what? Random variable. Then in number three, we say the error term. Though that one is always tagged constant variance. Constant variance. You see, the error terms is assumed to be constant over all the groups. Error term is assumed to be constant over all the groups or levels. These are what we refer to as the assumptions of the one-way ANOVA model. All the variables have to be normally distributed. All variables have to be independently and identically distributed. Then the error terms is assumed to be constant over the levels or groups. Thank you very much. Without wasting time there, let us progress. So these are what we call the assumptions of this model. The question becomes, how do we conduct a one-way or one-factor analysis test? How do we conduct a one-way or one-factor analysis of variance test? How do we conduct it? We conduct it now starting from what? The hypothesis. So the first thing there that we state the hypothesis. So procedure or stages of conducting one-way analysis of variance. Talk about procedure. Number one, we are going to state the hypothesis. And look at how to state the hypothesis. you say that H subscript 0, that your mu what 1 equals what mu what 2 equals up to mu k. That is that the mean of the population from group 1 is the same thing as the mean of population from group 2 down to the mean of the population from group K. So invariably we are saying that the mean of all the levels, the population mean of all the levels or all the groups are equal. That's the best way to put it. That the population means of all the levels or all the groups are equal. That is what you have written here. Then against H1, that you have H1, that mu I is not equals what? Mu j. Then for I not equal to j. So you are saying that the moment there are two population means that are not what equal, that this assumption here in the first hypothesis, H subscript 0 is already wrong or faulted. That the mean, the ith mean, population mean, ith population what mean is not equal to the jth population what mean, where I is not equal to j. Okay? So that is of course what we call the hypothesis. So that is number 1. Number 2, we say we state the level of hypothesis. State the level of hypothesis. State the level of hypothesis, which is always alpha, which at times could be 0.01 or 0.05, depending. It can take other values, depending. So the next thing here, which is number 3, is talking about that we define the test statistics. Define the test statistics. And here our test statistics F is given as what we call MS treatment all over what? MS error. We are going to know more about this MS treatment all over MS error. And this of course follows F of what? What we call V1, comma V what? 2 with alpha level of significance. We are going to explain what we mean by V1, explain what we mean by what? V2, when that time comes. Then number 4, we say that we are going to state the critical region. State the critical region. And of course, the critical region is F, this F here, greater than what? F of V1, comma V2 of alpha. Reject H0. So when we calculate this F from the table of ANOVA that will be given to us, and we read this one from F distribution table, which of course we are going to explain, and this one we calculated happens to be greater than the one that we read from the F distribution table, we reject H0. That the group, that the population means of all the groups are not equal. Then number 5, then we have what we call make conclusion or make conclusions. We are going to make now conclusions based on what we have seen here. These are of course the stages we are going to apply when we talk about one-way analysis of variance. These are the stages that we are going to follow. So permit me to clean here because our major concern is to take real life example and see how this thing goes. So permit me to quickly clean here. Then we now come to the most important thing which we want to discuss today. Very most important thing. And that is what we call, in the test statistics we wrote, we said that it is mean square treatment, MS treatment all over MS error. That thing is called mean square treatment all over mean square error. So we need to know how to calculate those things. And that's exactly what we are going to do speedily. So, and before we can talk about calculating it now, we want to show what is called what we call ANOVA table. One-way analysis of variance ANOVA table. One-way analysis of variance ANOVA table is going to talk about, I have here to be SV. SV. This SV is talking about source of variance. We talk about what? DF. Degrees of freedom. We talk about SS. Sum of squares. We talk about what? MS. We talk about mean squares. And we talk about F ratio. F ratio. Now, source of a variance in our previous class, of course, all the variance that exist in our data set in ANOVA is classified into two. We have what we call the between variability, and the between group variability and within group variability. So when we come in source of variance, we are going to have what we call between groups. Between groups. Okay? Then when we come here, we have what we call within groups. Within groups. And then when we come here, we have what we call total. We do a line like this. We talk about the degree of freedom of what? Between groups. Okay? So the degree of freedom here is what we call k minus 1. Then here is given as what? K into n minus 1. And here is given as what? Nk minus 1. That is degrees of freedom. Then here is going to be what we call SSTRT. Sum of squared treatment. SS error. This E stands for error. And then we have SST. Sum of squared what? Total. So here becomes what? For me to get MS here, for me to get this MS here, it is going to be SSTRT all over the degree of freedom, which is what? K minus 1. Here is going to be SS what? E all over degree of freedom, which is K into n minus 1. We don't talk about mean square total. So, and then my F ratio here now, this my F ratio here now, is now my F now is given as MS treatment, MSTRT all over MSE. That was that thing I wrote earlier, which I said that we are going to quickly understand. So the question is, how do we get the value of this? How do we get the value of this? How do we get the value of all these things? It's actually very simple. Let us speedily talk about it. For you to get the value of SS treatment, the formula is given as, we are going to take it gently, SSTRT, talking about sum of squared treatment, is given as, we have summation over I of yi dot all squared all over what? N minus y dot dot all squared all over what? Nk. And remember, we already have shown you how to obtain yi dot the other time. It's just for you to square it. And we have shown you how to obtain y dot dot. It's just how to square it. You know your n, replication. You know your k, number of factor levels. Then you now have that your SST, which is sum of square total, is given as summation over ij of yij all squared minus y dot dot all squared all over nk. For you to obtain sum of square total, this is the formula that you use. You know your yij, those observations inside there. You know your y dot dot squared all over nk. Okay? And we are told in our previous class that SST is the same, is equal to SSTRT plus SS what E. The sum of square total is equals sum of square treatment plus sum of square error. And don't be confused when you hear some people call this thing total sum of square, treatment sum of square, error sum of square. They are the same thing. Or some people will even call this one, which of course is what we wrote here, between group sum of square. So between group sum of square treatment or treatment sum of square is the same thing as between group sum of square. Then this one, which is error sum of square, is the same thing as within group sum of what? Square. Then here is a total sum of square, which of course is what we have here as a total. So whichever way they call that thing. I am calling it here sum of square total. Other people might call it total sum of square. They mean the same thing. Sum of square treatment, treatment sum of square. Sum of square error, error sum of square. So now that I have known this and I've known this, I can easily get this one by just saying that this is SS what T minus SSTRT equals SS what E. And my SST is this. My SS total what is this. My SS treatment is what this. So whatever thing I get from this one minus what I get from this one will give me my error. That's what we mean by that. So let us quickly take one example and show how these things are done, and then we obtain this thing together. Let us be fast about that. Thank you very much. Okay, so look at a question we have. That question goes this way. He gave us, he called here a treatment, he called here a rep, and then this treatment is talking about medication. This one is medication. This one is exercise. And then this one is diet. So we have this, we have this. This replication is 1, 2, 3, 4, and 5. So this one is I have here to be 10. I have here to be 10. Here is 12. Here is 9. Here is 15. Here is 13. Then we have here to be what? 6, 8, 3, 0, and 2. Then you have here to be what? 9. Here is 12. Here is 8. Here is 4. 1, 2, 3, 4. Yes. Here is 9. Okay. The first one is 5. Here is 5. Here is 9. Here is 12. And here is what? 4. So this thing stands for what they call reduction of they are using medication here, they are using exercise here, they are using diet here. All of them are targeted now to reduce the blood pressure. So they want to check whether there is any statistical significant difference now between the use of what? Medication, exercise, and diet in reduction of either the blood pressure level or the diabetic level. It was not exactly mentioned here whether it is talking about diabetic level or whether it is talking about pressure level. So our interest here is just to determine if there is any statistical significant difference between medication, exercise, and diet on this data, which can be coming from anything. Just like what we said earlier, we now have our solution. So in your solution, you come here, you write yi dot, then you now quickly write what is called yi dot. That yi dot means you sum everything here, drop, sum everything here, drop, and you sum everything drop here. They have summed it, and then the value they have here is, here they have 59, they had here 59, they had here to be 19, and they had here to be 8. Then remember we said you quickly put a line. For you to get the y dot dot, you sum everything here. So my y dot dot equals, when they summed everything here, what they got was 116. 116. Okay? So in your ANOVA table, you are going to come here and do something like this. For you to get your ANOVA table, you come here and you write S dot V. You do something like this. You write your DF. You write your what? Your SS. Then you write your what? Your MS. Then you write your what? Your F ratio. Your SV here, of course, is talking about the between and within, which of course you can talk about treatment or an error. So you can equally come here and you have something like treatments, or let me be using between group. Between group. Here we have what we call within group. And here you have what we call total. This degree of freedom. Remember that I gave you a formula before, that for this between group, the formula is what? K minus 1 for us to get the degree of freedom. So when you talk about K, you are talking about number of levels. How many number of levels are involved here? 1, 2, 3. So our K is 3. So 3 minus 1 will give me here to be 2. I gave you the formula of within to be what? K into n minus 1. Our K is already 3. Our n is number of replication. 1, 2, 3, 4, 5. So I have in place of this K 3 into 5 minus 1. 5 minus 1 is 4. 4 times 3 is 12. So here is what? 12. My total means 2 plus this will give me 14. So in an exam, somebody can say, if the total degree of freedom is 14, and the treatment degree of freedom is what? 2. What is the degree of freedom for error? Because remember what I said earlier, that this between group can be called what? Treatment. This within group can be called what? Error. So in that case, we are talking about degree of freedom of what? Of treatment, degree of freedom of what? Error, and degree of freedom of what? Total. When they equally ask you about the degree of freedom of between group, referring to the same thing. Degree of freedom of within group, referring to the same thing. Degree of freedom of what? Total, referring to the same thing. So they can equally give you degree of freedom of this one and this one, you get this one. Or they can give you this one and this one, you get this one. Or they can give you this one and this one, whichever way they ask you that, you'll be able to get that. So when we come to SS, SSTRT, I've given you the formula that SSTRT is given as, we have summation over I of yi dot squared minus y dot dot all squared all over nk. This is all over what? N. I will explain this thing because I've already explained it. Here your yi dot is referring to these observations. Your n here is total number of replication, which is 5. So if you want to obtain this SS treatment, you are going to say that SSTRT is given as. Here you have 59, you have 5, 9. But you are squaring it, squared all over. Number of replication is what? 5. You say all over 5 plus. The next thing is what? 19, all squared, all over what? 5 plus. The next thing is 38. You have 38, all squared, all over 5 minus. Your y dot dot, which is what you have here, is 116. So you have 116, all squared, all over. Your n is 5, and your k is what? 3. So 5 times 3 is what? 15. So the moment you evaluate this and subtract this, you have gotten your SS treatment. And from what they have here, the SSTRT is 160.14. So you can confirm by evaluating this to know whether it is going to give you 160.14. And then for you to get SS error, quickly come to SS or total. Get the SS total first. So you have that SST is given as summation over ij of yij all squared minus y dot dot all squared all over mk. That's the formula I use there. And then of course you know that this yi dot is referring to all these observations here. So what you are going to do now, it becomes that this equals, you begin from 10, you have what, 10 squared plus, here is what, 12 squared plus, you say 9 squared plus 15 squared plus this square, you enter plus 6 squared plus down to, so down to 12 squared plus 4 squared minus, this is y dot square, which is what you have here, all over this. So this becomes what? 116 squared all over 15. So they have evaluated this thing for me, and the value which they have here is 264.94. This is 264.94. So my total is 264.94. So for me to get this, of course, remember what I told you earlier, that our SST equals SSTRT plus SSE. So if I want to get that of error, this one will come over here. It becomes SST minus STRT. This equals to SSE. So I am going to say this minus this value here minus this value, and what they got it to be is 104.8. So you have 104.8. You can cross check it. So in an exam, they can give you sum of the square total, give you sum of square treatment, and demand that you find the sum of square error. Or they give you sum of square error, sum of square treatment, and ask you to obtain the sum of square total. This is what you have here. And our MS treatment is sum of square treatment divided by degree of freedom. So if I want to get what is here, permit me to quickly clean here. I'm trying to manage the size of this video. That's why I'm a little bit fast. If I want to get my MS treatment, so I'm going to say that my MSTRT is equals SSTRT all over K minus 1. So all over this degree of freedom, K minus 1, and K minus 1 has given us what, 3. So for me to get what is going to be here, it is this 160.14 divided by 2. So this thing becomes what? 160.14 all over 2. And the value which they have here is 80.07. I have here to be 80.07. You can confirm it. Then for me to get SS error, I will now be able to say that SS what error is given as what? MS error is SS error all over, my degree of freedom here is 12. That is this thing I wrote here. So which is K into N minus 1. So this thing becomes this value here divided by 12. And when this value here divided by 12, what they have is what? 8.73. We don't talk about this. And then for us to get this one, it is going to be MS treatment. Here becomes what? MS treatment, MSTRT all over MS error. And MSTRT is 80. So I have 80.07 all over. This error is given as 8.7. And the value which they have here is 9.17. 9.17. So this is actually how to obtain your degrees of freedom from this, your sum of what? Squares, your mean squares, and then your F ratio. And with this, you are good to go. With this, you are good to go. So permit me to clean here, and then possibly clean here. So finally, we are now going to get our what we call the value of our F distribution table. So, and of course, In that case, I have this thing to be, I have f of v1, comma what, v2. The level of significance they gave us 0.05. So this thing becomes f. This v1 is talking about this between group. So I have 2, comma. This my v2 is talking about the within group, which is 12. This is 12. Here is 0.05. From f distribution table, with these two standing at what, the numerator, and then these two are standing as what, denominator. So this numerator is degree of freedom for treatment, denominator is degree of freedom for error. The value they have there is 3.885 times. And we told ourselves earlier that when f cal, that if f is greater than f of what, v1, comma v what 2 of alpha, we should reject h0. Reject h0. That's what we said earlier. So in that case, our f has been this 9 point this. The f of this thing is this, and of course this is greater than this. So we are going to reject h0. That says that the reduction to these observations when medication, when exercise, and when diet is used are equal. We are going to reject that assumption that they are not equal. They say they are equal, but from what we have done here, we are rejecting that statement which they say that they are equal. I am so sorry for the little rush which I had at the end of this class. When I looked at the size of the video, I'm already seeing 1 hour, and I decided to hasten it up. We will be bringing questions and solving with you till all of these things become very familiar with you. Thank you very much for your audience so far.